Topic 7.2 in AP Chemistry in Unit 7 called Equilibrium is the direction of reversible reactions. In our one-pager of notes today for this section, I'm going to cover three kind of main points about what makes a reaction have what's called an equilibrium or an equilibrium constant. And then we're going to go over three kind of versions or the significant three types of K values that you can have. And they do look a lot like kinetics graphs, and we're going to tie in Unit 5 with kinetics into equilibrium in this video. All right, so let's just go back to what is a equilibrium value or a K value, capital K, and then what does it mean to be in equilibrium. So our reactants turn into products, and then you're going to have these double arrows. And above the double arrow, what we could add in is that there was a rate constant for the forward reaction, so I'm going to put an F, and then a rate constant for the reverse reaction, instead of using like ones and negative ones. And what happens when something reaches equilibrium is that the rate of the forward reaction is going to equal the rate of the reverse reaction. That's what makes something have an equilibrium value called a K value. In my previous video for 7.1, I actually derive how I get to this point with the K value. So what we would do is say the capital K, which is the equilibrium constant, is the concentration or pressure, but in this case, let's just say concentration of our products B over our A. And what happens is depending on the rate constant, this value right here, or the forward or reverse, the size of the K value, whether it's greater than 1, less than 1, or equal to 1, will change and be equal to a different value. So I'm just going to kind of put in here a little bit of how I got to that point. So I set those two rates equal. So you'd say the rate of the forward reaction, which means A turning into B, is going to be equal to the reverse reaction and then the concentration of B. So what I did in a previous video is I showed you that you can put these rate constants over each other like this, and then you would leave the concentration of B on this side and then put the concentration of A on this side. And that is what gives us this equilibrium constant, this capital K. It's a ratio of the rate constants, and I think that will be helpful when we look at sort of the significance of K values. All right, so the first thing I'm going to do is just give you the broad category in case you've seen these in a textbook. Maybe it's not even AP chemistry, it's other types of college level chemistry. But the K value could be greater than 1. We mean like any value above 1, no negative numbers here, and no, this case. This is where we would say the K is less than 1. And it could be less than, or just, it's just less than 1. And what I mean by that is means it's a decimal, okay, not negative. So these are decimal values. And then this is where K, you can say, is approximately or equal to 1. So if you want to just say approximately 1 or fairly equal to 1. And those are sort of the three significant values of K that can happen, and then the graphs that are associated with them. So let's look at each one separately at a time. So let's just focus on this one where we're saying that the K value is greater than 1. So what does that really mean? It means, if you have products over reactants, it means that the B value, which is this one, okay, I'm not going to put colors, but this is B, is in purple, and then this is in A. When you're at equilibrium, and I'll show you where that is with orange, when you've reached equilibrium, we'll say you've probably reached equilibrium, let's say maybe here at this time right here. And sometimes that'll be called like time 2 or something. I'm going to put a little red dash somewhere back here, just so you'll see why, and then that's going to be, let's say, time 1. And at time 2, we've reached equilibrium because the concentration of B remains constant and the concentration of A remains constant. So again, what makes something be in equilibrium at this position over here in the graph, so if you want to say like this is when it's at equilibrium, and you'll see I have another video coming where I'll show you a data table what this looks like. But basically you're saying that the concentration of B remains unchanged and the concentration of A remains unchanged. It's going to stay the same value along this flat part of the graph. And then back here, I would argue that this is where we have the kinetics chapter. So this is where you have kinetics, which in AP Chem is Unit 5. So that's where kinetics is. All right, let me go back over to here and keep talking about this specific value of this equilibrium constant. So how it also happens is that the rate constants matter. So the rate constant of the forward reaction is sort of like larger. So I'm going to kind of bold it. than the rate constant of the reverse reaction. And why that happens is because there's a forward push, and we get more products at what's called equilibrium. So what you might hear is that this is a reaction where it favors the forward reaction. So you could say stuff like this. You could say the forward reaction is favored. Forward, just going to put RXN. Reaction is favored. The other thing you might see too is that, at equilibrium, the concentration of B is greater than A, meaning that the products are, you can also say that this would be product favored. The other thing you could do is say the rate constant for the forward reaction is greater. So these are all things that we could say, so we put like little dots. So that's the kind of the main point. It came from here. This is true. This is another true fact. Here's another one. Let's add a sixth one here. And what we could do is say that the rate constant, the little k, rate constant for the forward reaction is greater than the, I'm not going to finish the sentence, hopefully you can add that yourself, greater than the reverse reaction. All right, so I'm just going to do is kind of go to the next one, and that's going to be the same kind of 6 things. First is that the K would be less than 1, meaning that's a decimal. And you can kind of think ahead too. That means that A will be greater concentration than B. So when you look at the graph over again here, this is our A. We could also be using what are called KPs or partial pressures, but let's stick with concentrations. It's just easier for this and is more common. And then you could add in that what would happen then is I'll go over here, your K value happened because your equilibrium K value, equilibrium constant, is again the forward reaction is there, and then I'm going to make kind of like this one bolded, just trying to give you a visual. That means that the reverse rate constant is larger. We would then argue that what's called the reverse reaction is favored. You might hear that reverse reaction is favored. Reverse reaction is favored. Or you could say that again, it's where reactants are favored. And then this happens, this all happens because the rate constant for the reverse reaction is greater. So I'm going to write that one last point right here, is that the rate constant for the reverse reaction is greater. And this is the rate constant, okay? Remember, again, at equilibrium, the rates are equal, but the rate constants are not, okay, at least with these two. So then on to the last one for our little one-pager of notes here, which I've tried to do in my video, is keep all of these to one page for you. So for K equal to 1 or approximately equal to 1, what we can do right away is just say that, I'm just going to say it right away, that neither because we've covered this, neither the forward or reverse rate constant is greater, meaning they're pretty close to being the same. And this also, you could say that neither the reverse reaction are favored either. So I'm just going to say neither. I'm just going to do forward or reverse reactions are favored, meaning it's not either side. They're both equal. And what that means is, I'll just kind of put it here, is if our big capital K, the equilibrium constant, basically the forward rate and then the rate constant for the reverse rate, the rate constant, they're pretty much the same. And then what happens is A can be approximately equal to B at equilibrium. And if you look at the graph here, we can see that. Now, there are some really great activities to do that you can use to kind of prove that these are like the 3 possible significant versions of K out there, whether it's moving water over or pop beads or rubber bands or modeling kits. But there's a lot of great ways to actually model out this process of having these 3 versions of K. All right, this all stems from this, again, being reversible reactions, meaning that they have a double arrow. The other thing, don't forget that this double arrow can look different. You can have like, the full arrowhead. That's the same thing as like a half. So just keep in mind, again, we just have our reactants, I'll say R. I did this another way, turning into PR products. And again, you have a forward rate and a reverse rate that you have to deal with. All right, it also ties in basically equilibrium with kinetics. And again, if you want to look here again, we can say like, maybe equilibrium looks like it probably is established somewhere around here, for this one, and then, you know, around here probably for this one. And then any time before that, oops, sorry, in red here, okay? Any time before that, if we pick a time, those concentrations here, and this is going to be important in the next video, these concentrations I'm kind of putting like big red dots here. Let's say right here and here, huh? Those concentrations are going to be what's called a reaction quotient. And then these concentrations, I'm going to put an orange dot, these are going to be our equilibrium concentrations, which are going to be our K. And so that'll tie in the next thing, which is basically how do we talk about this Q value? It's going to be called a reaction quotient, quotient that's coming in 7.3. And these graphs really help tie that in when we get to that section. All right, hope you found this helpful. Please like, subscribe, follow, comment, and let me know what you like about these one-pager of notes for each of these sections in AP Chem or in your college level class.